in terms of what you need to do. Again, the quiz is really here to be a pacer for you. What I mean by that is that it's going to very much sort of touch on the key ideas that we've covered, right? So that you are sort of assessing yourself. Are you keeping pace with the course, right? And not sort of prolonging sort of the ability to solve problems and so on and so forth, okay? So sometimes they're a little easier, sometimes they are not as easy, but the idea is that you're trying to keep pace with the course, ensuring that you're able to sort of get through the material at a reasonable pace. Okay, so use that as a pacer for yourself. I know that the process is probably a little awkward, but you know what? We'll try to see based on feedback, right? Unless you feel any right away that you want to share. Is there anybody that feels that the process can be enhanced by slight tweaks to it, like for next week? As I said, I'll extend the submission time to 5 minutes. But are there any other requests based on the experience we had?
Will we get the solution to the quiz?
Oh no, I'll go through them with you next week.
Oh, okay. Thank you.
I need just some time to just sit down and just go through them and grade them. But I said it's not from us, but I want to see where everybody went wrong, and then I'll go through the solutions with you. That's what I usually do.
Thank you.
Okay. Yeah. Okay. Are there any other questions? If not, then I want to sort of go on to the next module. Okay, this traditionally, the next sort of 2 to 3 sets of modules are probably the toughest for students. Some of you will find it really easy. Okay, and it's not that the concept is difficult, but more so students find it difficult because obviously there's the introduction and use of sine waves, and that's all we really do. We deal with sine waves. Okay, because we want to deal with sort of the analog transmission of signals. And when we represent that mathematically, this is where students have a bit more difficulty. But essentially, if you pay attention to what I tell you, there are only very few key ideas you need out of a sine wave. So I will talk about the amplitude, the frequency, the phase, right? Along with how we represent that mathematically. That's what we really deal with in terms of sine waves. So yes, there's going to be about 2 to 3 lectures that are a little bit more difficult. And once we get through the physical layer, then most students find the course takes a very drastic turn. Not that the course becomes simply very easy, but it's just that the approach to the problems are very different. So then once we get through that, we're calculating things like bits per second, latency, and so on. So it's a different type of computation that requires nothing with trigonometry or any of that sort. Okay, so that's sort of our approach for this. If you feel that you're weak at trigs or sine waves, right, bring and pull up the book, your Math 10 or Math 11 book, right, and just review that. But there's also other materials that I want you to review. Okay, so we're going now into the core, the course. We're moving away from all the sort of the very high level concepts, qualitative and stuff like that. We're going to now start off with a physical layer. We'll spend about 2 to 3 weeks on it. Right, then we're going to move into sort of the data link, the network, and then the transport. Okay, you see on this particular slide, right? Again, everybody see my screen share. Okay, there are a few supplementary material that I want you to sort of get yourself up to speed. There is the Appendix E from the textbook, okay, which I've extracted as a single PDF file for you, and I've uploaded that to D2L. Right, so if you go to D2L, and if you go to sort of the content. Right, and then if you go to the supplementary material, right, I've uploaded two articles, right? The first one is Appendix E. This you must read, okay? It will give you the necessary basis of how we want to deal with sine waves, okay? If this is very simple for you, that's awesome. But if you struggle a little bit in this, right, then I want you to read a little further than that, right, by sort of reviewing sort of maybe some Math 11, Math 12 type of material in terms of sine wave. Okay, but you should be able to understand fully E.1, which is the trigonometric functions, right, and how to extract the amplitude, the phase, and the frequency of a sine wave. Okay. Then the other thing that I want you to be comfortable with, right, you can skip E.2, but I want you to spend some time on E.3, which is the logs. Okay, so it's called exponent and logarithms. Okay, so if you did the take-home lab exercise last week, right, that was really an assessment, self-assessment that I want you guys to do. If you did it with ease, awesome, right? You're very well prepared sort of foundationally for the course. If you find a bit of struggle, I want you to spend more time on E.3, And again, if you find that you can't solve log problems, then I want you to just review again problem sets that you can find as part of your math 10, 11, 12 curriculum, right, that deals with a bit of logs, right? And you want to get your logs under your belt because, as I said, when you take the algorithms course, right, logs will come back again. Okay, so that's E.3. And so I don't know if all of you had a chance to get a copy of the book, but I posted the entire appendix on sort of D12. Okay, any questions on that? Okay. The second thing, right, that some of you has, it depends on who teaches it. So I don't know who's teaching it now. Every sort of instructor that teaches it has a different approach to it. Okay, I know that when Farnaz was teaching it, she's now moved on to teaching cloud courses. She was quite heavy on logs. Is it Thomas? Did you take it from Thomas Lacey? Thomas Maglieri, yeah. Okay, he's relatively new, and I haven't had a chance actually to. So Farnaz and I used to teach level 3 courses. So I teach datacon, she teaches algorithms. We've done that for about 6 years, I think. And then Farnaz moved away from that course last year to focus more on cloud courses, and then Thomas took over. I see. Okay, so the summation with Tom, right? Okay, so every instructor takes a slightly different approach, but then I would rephrase my statement is that I think that graduating from sort of a post-secondary degree or diploma, it's not critical, but it's essentially nice that you're able to manipulate logs. Okay, Lacey? And again, our use of it is very focused, right? We're essentially trying to say, if I take the log 2 of something versus log 10 of something, because I want to take base 2 or base 10 of a certain value. Okay, and we'll do more reviews as we get to it. But for now, I want you under your belt, right? Because this is the lead time you can catch up, right, foundationally, and be prepared for the course. Okay, so take a look at the appendix. The next thing that I want you to sort of deal with, right, is some students say, how do I prepare for this course, and so on. So if you have a copy of the book, right, you'll notice that at the end of each chapter, there is practice sets, practice problems, and so on and so forth, right? So every chapter has that, okay? The solutions are available to you, and they're not just the final answers, right? So this is point 2 here, right? If you go to McGraw-Hill Higher Education, which is this website here, MHHE, right, the publisher actually releases the solutions, and is step by step. So it's not just like a final answer. It's like showing you how to solve every problem. Okay, those are available to you free from the publisher, even if you did not purchase the book. Okay, but what the publisher made available to the students obviously are the odd number questions. But I'll say this, right? You guys are in computing, true? Right? You guys are quite well versed in search engines. Right? I think that you are able to find the complete set of solutions that have been released to instructors. The only thing obviously is that I cannot post it online for you. Does that make sense? Okay. So why do I tell you that there are solutions, there are problems? Because this is how you practice. Just coming to lectures and listening to lectures is insufficient. Okay, you need to be doing practice on areas that you will find that requires you a little bit more effort. So next week, I'm going to release to you assignment 1. So there are total 4 assignments. Okay, each assignment should take you roughly between 5 and 8 hours to do. So you get, as I said, about 10 days to work on it. Okay, and so the practice problems, right, will be helpful again, right, in helping you do the problems. Okay, any questions on that? Point number 2. Let me say this again, right? The entire solution is available to you, right? In fact, published at no cost to you from the publisher. The publisher officially publishes to students, right, the odd number questions. But I think, given that you're in computing students, you should be able to find the whole set of solutions available. Any questions on that? Okay, so then there is a third article that I posted, and this is optional. Okay, I don't know if you guys had a chance to click on it. It's called A Mathematical Theory of Communications by Claude Shannon. Just so you know, Shannon is very much known as the father of information theory. Okay, you cannot go through networking or communications without knowing who Claude Shannon is. Actually, my advisor at Cornell was actually a good friend of Claude Shannon. They all did sort of their PhDs in math, actually, either at MIT or at Harvard. But without going to the historical reasons of that, right? Claude Shannon in 1948, this was actually his master's thesis. So I like to post sort of the seminal documents for all of my courses, right? And I think this is the foundation. If you're interested in this field, it's quite mathematically driven, but it's nonetheless a very interesting read, okay? This was published in 1948, just so you know, right? And the question is this: why is Claude Shannon known as the father of information theory? Well, very simply this: he quantified what a single bit of information meant. You got to look back 1948. Information prior to that, if you start to think about it, right, was essentially through smoke signals, right? I mean, you think about that. If I were to come out to you and say, Rana, today is a very nice day. How much information did I just give you, Rana? How do you quantify that?
In terms of bits or in terms of the information received?
Exactly. So that's the question, right? If I go out to you and I just say this, right? So the entire IT world, right, took a change in direction, right? And I'm talking about information theory, not information technology, right? Because of this seminal paper by Claude Shannon. He quantified what a single bit of information meant. Because if I just meant information content, I said, today's a very nice day. Some of you who dresses for the weather may take that as a lot of very crucial information. Some of you who don't care about the weather will say, well, there's no information content. But the fact that we said this, right? Every character is 8 bits, right? Every sort of word is 8 bits and so on and so forth, right? We now can say that, right? The fact that I said today is a very nice day, right? That's about 6 words or so, right? And so on and so forth. Does everybody get that? And that revolutionized, right, how we looked at information that is being communicated. And then that resulted in obviously the bits per second and so on and so forth, right? This was all mapped out in 1948 by Claude Shannon. And we'll revisit some of his other works that followed based on that. But in any case, if you continue to pursue down this field, you should at least glimpse through this document, even if you cannot fully comprehend it. And then hopefully over time and experience, right, you can start to grasp, right, why Claude Shannon is very largely remembered, right, as the father of information theory. Okay, any questions on that? So I encourage you to read that, but you're not responsible for the material in between, but you are responsible for Appendix E, just E.1 and E.3, as well as obviously the practice problems along with the solutions that are available to you. Okay?
Sounds good.
So what is the physical layer? Okay, let's get started. We'll go for an hour on this and see how far we can get. Essentially, right, we care about the representation of signals of information. Precisely. I don't really care what your source of information is. In fact, I don't even care about the content. Data communications doesn't care about the content, right? At the end of the day, my goal is to transmit a signal at the physical layer. And there are 2 ways that I can transmit that. Either as an analog signal, which is obviously through the wireless signals that we transmit, right? And we're going to try to find a mathematical way to represent that, right? Or through some digital signals that you have been previously exposed to in Comp 2785, computer architecture, okay? If we look at sort of the model that we're looking at through the 5-layer system, right? Remember we said physical layer was hop to hop. Does anybody remember that? Not end-to-end, which means that every router that I get to, there's a potential change in the physical layer in terms of how I actually signal, depending on the medium types, which means that it could be wired, it could be wireless. Even within wired, it could be copper, it could be fiber optics, right? In wireless, it could be cell phone signals, it could be Wi-Fi signals, it could be Bluetooth signals, it could be NFC signals, and so on and so forth. So now what we care about fundamentally in the physical layer is how we use analog signals, right? And how we do digital signals. Okay, so this is a diagram that you'll see over and over again as we go on each layer, where Alice at Sky Research is trying to communicate, right, with Bob at Scientific Books, right? And in this case, we're going to focus strictly, right, irregardless of network you're going through, whether it's a local area network, wide area network, right? Doesn't really matter. Okay, I care about what the signal representation of the data is, right, in the form of an analog or a digital signal. Okay, so let me start off by saying this. The data that we transmit, right, obviously can be analog or digital. Can anybody give me a form of analog data? What's analog data for you? Where have you been exposed to analog data?
Sound, wave.
Exactly, human voice. My voice coming out of me is analog. True? I'm compressing my sort of lungs and the air between you and me. Right, exactly, voice. Human voice is analog, right? Can you imagine if I'm actually digital? I mean, we've gotten very good with that now because obviously we can have very high fidelity sort of audio signals like Siris and Cortanas and Alexas that sound very human-like. But if you go back 10 years, right, actually even 15 or 20 years, anybody use a sound synthesizer before? Like in the early days where there were sound cards called sound blasters and so on and so forth? Where effectively, right, if you listen to sort of digitized voice, right, it sounded very discretized, for lack of a better word. It did not have the tones. It did not have the continuity in tones. It was very sort of stepped in terms of the voice that was actually produced. But in any case, analog just simply means this, right? The information is continuous, and it's continuous, right, in amplitude. I'll show you some diagrams in a minute. Or it could be digital, right? You are probably more well exposed to digital data, I believe, in sort of your sort of ecosystem where you deal with data, right? Because you capture these days even sort of your cameras, your pictures, right, with digital sensors like CMOSs of your digital phones, cameras, and so on and so forth, right? Who actually takes pictures with analog film? Anybody here? Has anybody taken? I should ask. Has anybody taken pictures with analog film before, where you actually have to buy a roll of film, capture it, right, develop it, right, and then sort of get prints out of it? Okay, not in the last 2 decades. Yes, a long time ago. But if you ever, so there's a big push with digital photography. In fact, the photography that you guys do now are no longer called digital photography. Are you guys aware of that? The new term for the photography that you actually do is now called computational photography. What does that mean? So we went from analog, and then we went to a digital sensor, and we call it digital photography. But the photography that most of you capture off your modern day mobile devices is actually now called, under a new category, whether or not you're aware of it, right, called computational photography. Why? Does anybody take photography off your cell phones? Exactly. Precisely that. Okay? It's computational, right? Because we manipulate through signal processing, right? So if you're interested in all this stuff that I say, you can morph a picture of a cat into a dog, right? But essentially, the photos that you take digitally, right, goes beyond what is real. Has anybody seen a picture of Shenkai on Instagram? I'm making this up, obviously, right? But the profile image of Shenkai on Instagram, it's a perfect image. I mean, and I don't remember Shenkai anymore, but I assume, right? I mean, on Instagram, his profile, he has flawless skin, right? His tone is perfect. It's completely flawless. He's got no blemishes, right? There's an enhanced version. Well, I shouldn't say it's enhanced, but there is a not for real version of him as his profile on Instagram. That's computationally achieved, right? What I mean by that is that, right, between skin pixel to pixel, right, you are sort of extrapolating what the skin tone is and you're evening it out, you're averaging it out, right? So you get this perfect image of an individual. Okay, and obviously through the likes of AI techniques, right, we're getting even closer and closer, right, to that. But there's a strong push now in the analog world that actually imperfection is a beautiful thing. Right, digital photography is starting to lose its sort of allure because it's too perfect. It's not real, right? And most analog purists, right, are now pursuing back, right, sort of the art of achieving that analog, imperfect, pixelated, grainy type of image. But in any case, that's not our focus here. So the data, right, can be analog, like human voice. It could also be digital, like your digital music, right? Your digital photography, right? The idea is very simple, okay? Anything that's continuous form, that's analog, which means, right? I like to sort of show the students, right? If you can take a pencil and pen, right, and a piece of paper, and draw the signal without lifting your pencil once, that's an analog signal, okay? Which means that it has an infinite number of steps, right, where you are smoothly changing the intensity of the amplitude. So the Y value that you see here, the value, right, that's amplitude. If you have to have discrete steps, as shown here in the B diagram here, right, where obviously, right, these vertical lines don't really exist, really, right? What we care about are these levels, right? Level 1 here, right? Level 2 here, level 3 here, level 4 here. Okay, the horizontal lines are just sort of visual for you to see the change in discrete values. That's digital. Okay, so anything that's smooth and continuous, that's analog, right? Anything that is sort of discretized, right? That's digital. So there are two things that are being exposed here, right? In the first slide, right, I said that the data can be analog or digital, right? Because that's the source of information, right? So data is the information content. Okay, the signals, right, are what we can actually transmit. So we cannot really transmit data. Okay, and it will become more apparent. I want you to start thinking about that. Okay, why is that we have to have signals to represent data? Okay, and it may not be the most apparent for you now, but I want you to understand that the data is the information content. The signals are what we use to transmit them, which is to transmit the data. Okay, and I'm saying that in both cases, both the data and the signal can be digital and or analog. Okay, any questions on that? And then I will show you, once we get through the introduction to analog signals and data, right, we'll look at the conversions, right, and why is it that we need to have signals transmit the data. But it requires a much deeper understanding before we can actually sort of describe to you in a meaningful way. Okay? So if we have sort of these types of signals, okay, which is analog and digital, and here we care about, because we're in the physical layer, right? I don't care about the data. The data is the information. I care about how to represent a signal to transmit that data. I'm now going to say that a signal can be both periodic and non-periodic. Okay, so what is a periodic signal? A periodic signal just says this, right? This signal, right, has a pattern to it, right? And the pattern itself repeats over and over again. Okay, each time we repeat this pattern, right, we call it a period, right? And the complete repetition is called a cycle. Can you give me an example of a periodic signal? When have you heard periodic signals? And obviously, right, the converse of that, right, which is a non-periodic signal, it just means that the signal has no exit-diddle sort of a pattern to it. Right? So if a signal repeats itself over infinite time, that's not a periodic signal, because you're right, there's no measure what infinite time really is. Right? And you should not have multiples of infinite time. Can anybody give me an example of what a periodic signal might sound like or be like? Sine wave, sure, right? So how is sine wave perceived in audio? Let's assume I say this, right? Today is a good day. 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 Is that a periodic signal? You can respond to me in the public chat, okay? For all of you, right? Because otherwise I have to keep flipping between different users to see the messages. Yes, exactly, right? That's a periodic signal, okay? But going back to sort of what Yongjun said, sine wave, right? A single tone like this. If I go and make a tone and goes, can everybody hear that? That's also a periodic signal, okay? So very simply, right? A periodic signal is nothing but a signal that keeps repeating itself, right? The same pattern over and over again over a finite time. Okay, The time that it takes to complete this pattern, right? And I'm giving you terminologies here, right? It's called the period. The time it takes for one complete cycle. And the completion of this periodic signal, right? Each time that it occurs is called a cycle. And the converse of that, right, is a non-periodic signal, which means the whole sort of lecture is sort of non-periodic, right? If I take the context of the whole lecture over 4 hours, because I don't repeat the same lecture 4 hours every 4 hours. You could claim that I might repeat it for the afternoon set, but it's a slightly different repetition, right? Because it's done in real time. Okay, so in that sense, you cannot really say that that's actually a periodic signal. Okay, so here comes the first equation I want you to be aware of, right? There is the notion of period, which is the time it takes to complete one cycle, right? So if I say this, right, I'm going to say boom, 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 right? So in about 1 second, I made 4 tones, right? The period to sort of create one tone, it's 1/4 of a second, right? I just made 4 tones in 1 second. That's 4 tones in 1 second. Each tone takes 1/4 of a second. That's the period. So we measure period in seconds, okay? And it's the amount of time it takes to complete one cycle. Now, the number of times that it occurs in 1 second is called frequency. So the frequency is 4. So if I made 4 tones in 1 second, right, the frequency is 4, it's 4 hertz. Is that clear? Simply, right, the relationship between period and frequency is nothing but the inverse. I'll give another example. So I want you to sort of you to be aware of this, right? Is that if I take 4 steps every second, is that frequency or is that period? If I take 4 steps, exactly, frequency. Okay. The period for me to complete one step is. So if I take exactly 1/4, right? But 1/4 in, oops, sorry, I'm on the wrong, yeah, exactly 1/4 second. Okay, is that clear? Okay, so throughout the course, I'm going to use these terms interchangeably. Not that they're exactly the same thing, but they're in fact just an inverse relationship between the two. Does that make sense? Right. So if you have period, right, the inverse of it is the frequency. If you have frequency, the inverse of that is actually the period. Okay, and then you need to be very, very careful with units now, right? Period is measured in seconds, right? Frequency is measured in hertz. Okay. So to give you an example, right, in real world, right, the power that we actually use, right, has a frequency of 60 hertz. I don't know if you guys are aware of that. So the AC current that you come in, right, comes in at 60 hertz per second. Okay. Do you guys know what this 60 hertz is used for? In a television set, a modern day television set. Has anybody bought television and it tells you that the refresh on the television is 60 hertz or 120 hertz? Some of them are now at 240. I've seen 480, and I've actually seen some television sets refreshing at 960 times per second, especially if you're one of those 3D televisions. So it's 480 on each channel, left and right, in terms of your stereo 3D channels. Has anybody seen that before? Yeah, so that's off a different clock, right? So your computer monitor refresh, right, is doing that 144 hertz. But television sets, right, if they're on multiples of 60 hertz, they're actually using the AC current as the clock, right? If you recall back to 2785, which is computer architecture, you've been exposed to the notion of a clock, right? A clock is nothing but a repeatable sort of up and down signal. Okay, so modern day television sets actually use the AC current as the base clock. So that's why your refresh rates are 60 hertz, 120, and so on and so forth. In Europe, right, in different parts of Europe, right, the frequency is 50 hertz. And so their refresh rates are 50, 100, 200, and so on and so forth. They're not any worse than sort of the corresponding television sets here we have in North America, but simply just because the clock is different. So they refresh a little slower. Okay. But the point I want to drive here is this. If I tell you that the frequency is 60 hertz, right, then I can obviously find the period by taking 1 over 60, right, which in this case will result in about 16.6 milliseconds. Okay, so that means, right, the period, right, for the power, which is the AC coming in, right, each of these cycles take about 16.7 milliseconds, right, in time to complete. Okay, so that's the notion, the first thing that you need to know. Now, let's take a look at the analog signals for now. Okay, my hope is that we can get through some of analog signals today. We won't touch on digital signals today, but let's just focus on analog. Okay, why do we care? Is analog useless now? I mean, is it gone? Or is analog still going to be around? I know that you guys do a lot with digital, but is analog gone or is it outdated? Exactly. So the Shankai is absolutely right. The world we live on is actually completely effectively analog. I'll give you an example. Can you try to blink your eyes in a discrete fashion so it's either open or closed? Is it possible to achieve that? No, exactly. Okay. Can you imagine driving on square wheels? Like, let's assume your car was installed with wheels that are not round but square. Would that be a comfortable ride, Yongju? No, but have you tried? I mean, you could try. If you go back to the Flintstones, right? I believe they have non-perfect round wheels, right? And obviously the ride is extremely bumpy. Okay. So the world is predominantly analog, just so you know, right? This digital has its limitations. Digital has its advantages. We'll touch on the why we are moving towards digital signals in our sort of day-to-day life. It's really for efficiency, and in fact, it's a representation of the analog world. Remember, right? The analog world is where information is continuous, right? In terms of the signal, right? It has an infinite number of levels. Discrete levels, right, are stepped. Okay, but I want to extend this whole idea of an analog signal to simple waves versus a composite wave. Okay, let me define for you that first, and then I'll get you to understand why we care about this. A simple wave, right, or a simple periodic analog signal, it's a wave where you can no longer break it down into even more simpler waves. In our representation throughout this course, this will be a sine wave. Yeah, let me say that again, right? A simple wave is one where you cannot further decompose into even more simple waves. So in our context, right, that's a sine wave. A composite signal, right, is one where it consists of multiple simple waves, right? Which means we're taking multiple simple waves that are being transmitted, and then we're aggregating them in time to become a composite signal. So can you give me an example of a simple wave and its corresponding example of a composite? What is a simple wave that you've experienced in life? And what happens when you aggregate those simple waves? Can you give me a corresponding example of what that composite could be? Anyone? Someone. Who's been to a concert hall? Who's been to a concert? And when a concert, I should say that. Rephrase that. Concerts are a little too composite for me. Anybody been to a live orchestra performance? Has anybody seen an orchestra perform with sort of the violins, the cellos, the double bass, the clarinets? Anyone? Nobody? Somebody must have, right? Has anybody, well, not live, has anybody heard an orchestra before? Like, have you heard a symphony perform even on audio? Okay, good. So if you start to think about what an orchestra is, right? In fact, every instrument is capable of producing single tones. True, if you press a note on the piano, that's a single tone, right? The collective tones from stage, from the different instruments, in fact, becomes a composite signal. Let me say that again, right? If you start to think of what simple versus composite really means, and I will give you an analogy to real life, right? Imagine instruments on a stage that are playing single tones each. So the violin is playing a tone, the cello, the double bass, the clarinets, right? The pianos, right? The harps, and so on and so forth, right? Every instrument, imagine for a minute, right? That plays single tones. But assuming that you're the audience in the concert hall, right? All these single tones actually travel independently to your ears. True, like when a piano plays a tone, right, it's traveling independently to you. When a violin plays a single tone, it's traveling independent to you. Okay, so now, if these tones come to you, right, because they travel independently and they come to you, and obviously, right, you will perceive and aggregate them in time, and that becomes a composite signal. True, because you're hearing multiple tones together. If these tones sound pleasant to your ears, you call them music. True? Now, what if these tones coming to you does not sound pleasant to your ears? What do you call them? Noise, exactly. Okay, so you decide to think about it, right? In fact, effectively, right, this is what is happening here, is that we have single tones and single simple waves, and we are trying to create a composite of these waves, right, to become that of a composite signal. If they come close, if they come in aggregate in time that is pleasant to your ears, so the violin, the clarinet all playing at the same time, right, that's music, right? And then if they don't sound pleasant to your ears after they're aggregated, then they're called noise. But these days, what you hear is questionable, right? I mean, what you call music, right, may be noise to others. Isn't that true? Right, Yongju? Right? Is truly what you listen to music, or is it actually noise? Okay. The other point that I want to sort of make is this: has anybody wondered, why is it that if you ever go to a live concert, right, and this could be an orchestra, a concert, you know, whichever you choose as your source of music, right, why are some seats priced at $500 and some seats priced at $20? Why? What does that mean? It's obviously the quality, but what does that mean? Why is that? Why is it that some seats, when you go to an orchestra or a concert, right? Obviously, right, there's a proximity to the performer that, you know, the closer you are, maybe you're paying a little bit more because you get a close-up look of the person, right, or the individual, the performance. But what else? It is sound quality, but what defines sound quality? Exactly. Precisely what Yongju has said, okay? It's not, yes, so it's the proximity, right? But the signal is transmitted as it is. What does that mean? Remember, right? The point I'm trying to drive here is this, is that the instruments produce single tones. Usually in an orchestra, there's a conductor that sort of signals to all of the performers on stage on the different instruments, right, the timing of the music, right? So every note coming together, interaction with the other note from a different instrument, and so on and so forth. But notice, these simple tones, or these simple analog signals, travel independently. So as they are emitted from the stage, they could be taking on different speeds because of different velocities, right? They could be taking on different distances because some of them may bounce off the ceiling, some of them may bounce off the side walls, right? If the sound aggregates at the receiver, which is your ears, at the exact same timing as it was being played on stage, which means as it was intended, right, in Yongju's terms, then that is a reproduction, right, a very accurate reproduction of what was intended. Those seats cost a lot of money because you get a true reproduction of it. Now, obviously, right, because of the layout and the acoustics of the room, not every seat is going to get that very accurate reproduction, right? And therefore, their price lower, which means that the tones between instruments could be slightly offset in time, but not enough to distort the music in a way that it's a different piece of music, but enough that it's not a pure reproduction of what was intended on stage. Okay, is that clear on what that is, right? So the point I was trying to get at, right, is that we're in analog signals, right? But within analog, right, we're breaking it down to two sort of categories of it. One, which is obviously a simple tone, and one which is a composite, right? Simple tones are emitted and aggregated in real time at the receiver because they travel independently. Composite signals do not travel as a composite. I do not go up and say, you know, I'm collecting all of these tones that I created on stage and then feeding that down through a pipe, right, and then directly to you. I let it bounce around the surroundings. And by the time that it gets to you, the composite signal could be an exact replication or could be a slightly off, right, in terms of timing, in terms of replication, right? And that is why, you know, in concert halls, right, some seats are priced at $50 and some seats are priced at $500. Okay? So this is the sine wave that we'll be dealing with for the entire course. Okay? Has anybody seen this before? I think this goes back to around maybe grade 9, maybe grade 10 or grade 11. Okay, but we're going to now mathematically define this, because for everything that we do, right, we're going to take a mathematical approach. As I said at the beginning of the term, right, this course is a quantitative approach. The reason why we do that is so that we can actually manipulate the characteristics of the sine wave, right? And that's what essentially signal processing is all about. So the DigiPro option students, right, will take a sine wave, right, or a mathematical representation of what the wave is, and obviously, right, morph it in some way. Okay, what you guys do now these days, right, in terms of your real world application, right, of signal processing, right, is to take something that is real and make it unreal. So the case that I said, right, I believe I said it was Edward, maybe, I can't remember who it was, but let's say it was Chantel, right? Her Instagram profile, right, is not really her. And what I mean by that is that it has been morphed in some way, right, to go from something that's real, right? So there's obviously slight uneven skin. I don't know Chantal. I've never seen her before. I don't even know if I saw her in the first class. But let's assume that she doesn't have quite the perfect even skin tone. But you could take the averages of your skin tone and your display image, make that, right, even. But you can go further than that, right? You can do signal processing to say this. In fact, I'm going to change the tone of my skin. So I could go into a lighter shade and I could go into a darker shade, right? So that's what computational photography signal processing is that it goes from something that's real to something that's perfected, and then to something that's actually not even representative of what we have. But in any case, we want to find a mathematical representation of this sine wave, right? Which is nothing but something that goes up and down, up and down. And mathematically, it can be defined as this equation. Okay, so I'm going to do the presentation here. So I'm going to rewrite this for you. Okay. I'm saying this, right? Given a sine wave that looks like this, okay, I can mathematically define, right? So I'm going to do time here, right? This is time, right? This is amplitude. Is it because it's lunchtime? Okay, bear with me. You've got 28 minutes to go, and we'll see how much we can go from here. Okay. When I say I want to mathematically define this, right, I really mean this, right? I'm going to take this sine wave as y with respect to time, right, because of this time here, right, is equal to a sine 2 pi ft plus theta. This is the mathematical representation that we'll be using throughout this course. Okay, this y of t represents the changing amplitude, right? So this is actually your amplitude, right, which is a y of t. I'm saying that this is a changing value with respect to time, right, which is why it's taking on this argument. Okay, so there are a couple of things here. Okay, the amplitude here, right, is the peak amplitude. The value here, A. The frequency here, right, is the number of oscillations per second. So if I say all of this happens in the time frame of 1 second, then F equals to 1 hertz. Okay, and then the theta here, right, tells you how much with reference to time equals 0, right, your sine wave has shifted. Okay, so really, these are the only 3 things I want you to know about sine wave. Okay, and if this is very foreign to you, Appendix E.1 will give you a much sort of clearer sort of repetition of what I just said. Okay, I want you to know that A is your amplitude, right? And this is the value that I care about, the peak amplitude. Okay, and it's measured, obviously, right, in volts. Frequency, right, is the number of cycles you have, right? So this is frequency, and is measured in hertz. Okay, and then theta, which is actually the phase shift. Okay, and this is measured, right, either in degrees or in radians. Okay, so if we go back to this diagram here, right, so these are really the three parameters that I want you to be aware of, right? Your amplitude, your frequency, right, and then your phase shift. Does everybody follow? Okay, if this is very foreign to you, right, I really urge that you take a quick look at E.1 after this class, because we're going to spend about 3 weeks, and this is usually what throws everybody off. Now, so we use this sine wave to mathematically represent what we want to transmit. And the question is, why do I want to change the values of A, F, and theta? Why? I'm saying this, right? If I use a sine wave as a representation of an analog signal, there are effectively 3 degrees of movement that I have, because I can change A alone, I can change F alone, I can change theta alone, or a combination of these. Which means, right, if I show you a very simple change in amplitude, that's the easiest one to see. If I say, if there's a sine wave, right, that goes like this, right? And this is obviously with respect to time, and this is A equals to 5 volts. Versus another sine wave that looks like this, right? Where A now, right, equals to 10 volts. Everything else being the same. So it has the same frequency, right? It has the same theta, phase shift. So this I did not change, but I simply changed the amplitude. Why do I want to do that? What's the purpose of that? What does it gain for me? Anyone? Why is it that I want to have amplitude equals to 5 and amplitude equals to 10? So let me ask you a question. When you transmit an analog signal being sent, sure, the amplitude changes. Clearer signal is potentially it. But why? There's one critical reason. Remember, right? What is data in sort of the digital form, right? Data is really logical ones and zeros. True? True. I mean, everything that you're receiving over your Wi-Fi, right, as part of digital data is represented previously as ones and zeros. But we motivated in the first class, right, that nobody, at least nobody publicly, exactly, nobody publicly acknowledged to me that they can see ones and zeros fly through the air. Is that true? Does anybody see ones and zeros fly through the air? I mean, if you have, you can tell me privately. But my recollection from the last class is nobody saw that. So then how is it that we're being able to transmit as a signal over Wi-Fi? Right? Yes. All those are yes, right? So effectively, right, I'm saying this. Shenkai, I'm going to send you some information, right? I'm going to send you the bit sequence of 101011. Right? So this is the data I want to send you. And I'm going to tell you this. Well, I'm going to send you sine waves because it's analog, right? So if you receive something that has a peak amplitude of 5 volts, it's a logical 1. If you receive something with a peak amplitude of 10 volts, that's a logical 0. Does everybody follow? So what Shankai does is he sits there as the receiver, which is your Wi-Fi adapter, and you're measuring the amplitude of the signal. So if I want to send 101011, I'm going to send 1 at 5 volts, then I'm going to send 0 at 10 volts, and I'm going to send this guy again, and I'm going to send this guy again, and then I'm going to pulse this twice. And then I can do the same for phase shift. I can do the same for frequency. I can do so there's many degrees of freedom I can actually do to manipulate the sine wave to achieve the sending of ones and zeros in my system. Does everybody get that? So there's a lot more to it, and I'll slowly sort of decipher that for you, what the gaps should be, because of somebody say, right, I want, obviously, right, would it make sense to transmit 1 at 5 volts and 1 at 6 volts? This is 5 volts. Exactly. Why? I'm telling you that this is 5, right, and then this is 6. The room for error is minimal. Does everybody see that? So really, I want the greatest amount of separation, right, between what I transmit as a logical 1 and what I transmit as a logical 0. Okay? So that's really the basis of what we're trying to accomplish in analog signals, is that we want to use, right, this sine wave with 3 different characteristics. In fact, there's a 4th characteristic called the wavelength. We'll talk about that later, but we don't use that in this class. But I'm saying this is that if I take a sine wave that I presented to you here, okay, which most of you have seen as a student, in this course, we're going to extend that one step further, right? And we're going to take a look at its mathematical expression, right? Where there are 3 degrees of freedom I can manipulate to represent the data I want to transmit as a signal. And the 3 degrees of freedom are really its peak amplitude A, its frequency F, and its phase shift, right, or phase, right, called theta. Okay, so then if I show you a time domain plot that I've been sort of illustrating on the whiteboard, right, is this. I have now a sine wave. So we know fundamentally a sine wave is up and a down, right? So the peak amplitude here is 5 volts. So the A equals to 5 volts. I need you to be able to extract that. Okay. Now, if all of this happens within 1 second, then the frequency is 1, 2, 3, 4, 5, 6 hertz, which is 6 hertz here. And then the phase shift is 0 because with respect to time equals to 0, right? This now is starting at 0. And so if I start to manipulate these parameters, I will get a different sine wave, and I can use that difference to represent a different symbol. Is that clear on what we're trying to do here? So I want to lay out why we're actually doing this so you're not lost just in the math. Any questions? So as I said, again, as with the physical topologies, there are pros and cons of using amplitude, pros and cons of using frequency, pros and cons of using phase. And we'll take a look at that in a few minutes. Right? Or a combination of these. So this is an example of a high amplitude signal versus a low amplitude signal. Right? In my illustration that I gave you, I said this. Well, I could use this high amplitude to represent a logical 1, and I can use this low amplitude to represent a logical 0. Right? And obviously, right, there are some considerations as I want to deal with in using this high end versus low. First of all, there should be enough differences between the 2 amplitudes. Why? Because imagine, right, if I say I transmit something at 5 volts, and I transmit it over a distance, do you think the receiver will receive it at 5 volts? Let me ask the question again. If I say I'm transmitting a signal at 5 volts, and I'm transmitting this signal over a long distance, do you think the receiver will still receive it at 5 volts? No, that's the answer. So the amplitude, you can think of that as the volume. So if indeed, there will always be losses. There will always be. Right? So if you think about this in a classroom setting, unfortunately, I cannot demonstrate it here in this sort of a remote setting. But let's assume you're seated at different distances apart from me. So you've been to a lecture hall, you've sat very close to the faculty, and you slept very far away to the faculty. True? right? When you want to do your online gaming in class, you sit very far from the instructor. When you want to sort of listen very closely, you tend to sit closer to the instructor. Is that true, Youngju? Is it fair to say this then, right? Is that when you are seated close to me, you get a higher volume of my signal than as compared when you're seated far away from me. So if you're seated at the far corner, right, in fact, what you hear is probably a lot of noise than my signal, because everybody else talking in between me and you, everybody else eating the lunches, eating chips, right, that all adds to the ambient noise. And obviously, my signal itself degrades over distance because there's resistance in the air. So as my energy, even if it was a perfectly quiet room, my energy will dissipate. The person that's seated furthest away from me, given that you have the same pair of ears in terms of sensitivity, will always hear me at a lower volume than the person actually seated in front of me. So part of the reason why we don't always use amplitude is because of its dependency on distance. So why I want these two amplitudes to be far apart? Simply this: if I say this was 5 volts and this was 5.5 volts, well, the amount of perturbation of this signal as it travels through distance is enough for me to incorrectly receive it, right? If this was the top diagram at high amplitude is a logical 1 and this is a logical 0, right? The distance is enough for me to make an error in determining, right, whether it's a 1 or a 0. Does everybody see that? Okay. So let's take a look at frequency. So if I say this, okay, frequency is the number of cycles that I have within a second. So in this case, it's 1 second here, and there are 12 peaks. Well, then the frequency is 12, right? And then I can say, okay, well, because it's 12, then obviously the period is 1/12, right? 1 over 12, right? 1/12 of a second. And then I can have another frequency of 6 hertz, right, with a period of 1/6. Then I can say this, Yongju, instead of you sitting there and measuring the amplitude of my signal, right, which can be inconsistent depending on your distance between you and me, and so the sender and the receiver, I want you to sit there now and measure the number of peaks that comes by to you. So in this case, right, if it's a logical 1, I said that you're going to count 12 peaks within 1 second. If it's a logical 0, you're going to count 6 peaks. Does the change in amplitude matter here? Meaning that, does distance come into play here? Is it something? No, exactly. Because it doesn't matter as long as the difference in amplitude will be impacting both the logical 1 and 0 equally. Which means that if there's a change in amplitude, it will impact both logical 1s and 0s, right, as much. So as long as it doesn't degrade to 0, which means Yongju can no longer count the number of peaks, he can safely determine whether there are 12 peaks versus 6 peaks every second that goes by to determine whether it's a logical 1 or a logical 0. Does everybody see that? So that's for me to use frequency. What would be a disadvantage of this scheme? This you may not know, so I'm going to share it with you. So has anybody heard of something known as spectrum? Right? So you know how everything that you sort of transmit over the air, you have to pay a license for? So like, for example, in FM radio, 94.5 is allocated to radio station 94.5, 94.3, 96.1, and so on and so forth, right? Spectrum in a wireless sense is very expensive, right? Auctions for spectrum by the telcos like Telus, Shaw, Rogers, right? They buy spectrum, blocks of spectrum at billions of dollars. Right, so they're licensing it from the sort of the FCC, right, or the Canadian equivalents of the FCC. Okay, so the problem is this: if I use frequency to differentiate between 1s and 0s, is great. But now I need to use so amplitude is no longer really a concern for me until it becomes 0. But it becomes a very expensive proposition to try to say that I'm going to create this many different number of frequencies because I may not have the bandwidth required. Okay, so again, pros and cons, right? So that's as much as I want you to know. So there was the use of amplitudes, right, high and lows. There's the use of different frequencies, right, each with its pros and cons. And then obviously there's a third way I can do, right, is to use phase shift, right? And I said phase shift is nothing but sort of your relative position in time, with respect to time equals to 0, right? In this example, I can show you that there is a phase shift of 0 in the top diagram, a phase shift of 90, right, in the second diagram, right, because you're moving 1/4, right, of a sine. So a sine wave goes from high to low and then back to 0. This is 360. So the midpoint is 180. This peak here is 90 degrees. This peak here is 270 degrees. Okay, so I could have a 90 degrees phase shift, or I could have 180 degrees phase shift. So this is 0. This is coming down at 90, and then this is going at 180. Okay. So does frequency matter in phase shift? Do I need to consume more frequencies? Because look at all of these. Do all of these signals have the same frequency or different frequencies? Same or different? Exactly, right? So frequency doesn't really matter. Okay. Does amplitude matter if I'm trying to find out what phase you are transmitting at? No, exactly, right? So this is the third dimension, but the problem though is this. There is a difficulty with using phase to differentiate different values. And the reason is this, is that I need to know what your reference to 0 is. Remember, right? What I receive, right, is a different time than when you transmitted it. True? I don't get it instantaneously. I get it momentarily later. Right? We perceive that it's almost instantaneous, but it's not really instantaneous. So what I'm driving at is that now if I can go with frequency, right? If I can go with amplitude, but I could also go with phase. But the problem with phase is it has no dependency of amplitude or frequency, but it requires me to know what your time equals to 0 is. So that became difficult in the early days, but we've gotten so good with it that LTE is basically, right, trying to monitor both the changes in amplitude and in phase in a scheme we call SQUAM, a QUAM. Okay, so it was difficult, obviously, right, to do that in the past, but we've gotten much better at being able to do that now, right, and therefore higher and higher data rates. Okay, so if I go back and obviously this is just a note I want you to know that, right, within every 2 pi radians, right, is 360. That's one complete cycle, right, of a sine wave. So let's go back to say this diagram here, because I want to sort of give you an idea of why we're doing all of this. Okay, so remember, right? I told Yongju you can use the top wave to represent a logical 1, and you can use the bottom wave to represent a logical 0. True, Yongju or Rana, whoever is sort of willing to respond. Okay. So which means if I send you one at this amplitude, it's a logical 1. If I send this to you at a low amplitude, that's a logical 0. True.
Yes.
Which means each time you're receiving 1 bit. Now, are you happy with a system that is at 1 bits per second?
Definitely not.
Like, who would be? Anybody here? Can you imagine you're transmitting at 1 bit per second? Right? It would take hours, right, for me to send one sentence to you. So how do you think we can achieve higher data rates? Which means higher data rates means I want to transmit more bits at a time. How do you think that can be achieved?
Frequency, increase the frequency.
No. So this is the biggest misnomer. Frequency does not equal to data rate. And forget about frequency, forget about phase, just focus on amplitude. How can I transmit more bits at a time? Multiple ways, exactly. Let me show you that. Okay. Let me just move to a next slide here, okay, and I'll show you what I mean by that. And then this will be sort of analogous to the frequencies, to the chart, right? I said this, right, in the beginning, I said this, okay, you know what? I want you to have now this, right, at A, right, to be a logical 0. And then I have this guy here, right, to be this, right? This is terrible. This should be like this, right? And then this is A2, right? So this is the logical 1. True? Does everybody follow? So this is A1, right? This is at a certain peak, and then this is another peak, and then this is a 1. If I want to send 2 bits at a time, what can I do to this wave? So this is representing, right? If you receive A1 as an amplitude, right, you're a logical 1, a 0. If you receive A2, you're a logical 1. Yongju says multiple waves. How do I get multiple waves here?
Different amplitudes.
Different amplitudes, which means 1 bit, 2 waves. 2 bits, how many waves?
4.
4. Does everybody see that? So effectively, right, I can say this. I can have 1 wave at this amplitude A1. I can have a second wave at A2. Right? I can have a third wave at A3. And then I can have a fourth wave at A4. Does everybody follow? Then I can go back and I can say this. If you receive at A1, this is a 0, 0. And if you receive at A2, this is a 0, 1. You receive at A3, this is a 1, 0. And if you receive at A4, this is a 1, 1. Does everybody follow that? And if I want to send 3 bits at a time, how many waveforms do I need? No, 8, exactly.
Right.
No, 8. 8, right? 2 to the power 3, right? Okay. So can I have infinite data rates? Shankai, we'll talk about all those interferences and so on and so forth at another class. We'll talk about the impairments and so on. But let's just focus on the signal generation first so that we don't complicate things. Right? We'll address that probably not next week, but the week after. Okay, Shankai? So can I have infinite data rates? Can I have infinite number of levels? Can I keep increasing this until I have infinite levels? No, why not? Not bandwidth. Bandwidth is the wrong word to use. Remember, we're only voltage, exactly. We don't have infinite power. We don't have infinite power, right? So I cannot have infinite number of levels to give me infinite data rates, which means I'm capped. In fact, right, my constraint is this. If I have a system, okay, and I'll end on this note so that you guys can take off for today, right? And this extrapolates to obviously the same thing as frequency and my cap is this. If I have a system, like including your mobile systems, right? And I say this, you know what? The maximum voltage you can transmit is 5 to minus 5. Now, you can say, I can try to create an infinite number of waves in here. Right? I can do an infinity. I could have infinity number of waves here. But what is the issue if I have infinite number of waves in there? Versus if I have a system, right, and I'm just drawing another sine wave here, I can have 1 wave here, 2 waves here, 3 waves here, and then 4 waves here. What is the difference?
The error margin of the first one is way more than the second one?
Exactly. Signals are too close to each other, which means at some point, remember I said this, right? Even if you perfectly transmit at this level, you're not going to receive that because there's going to be some perturbation. So effectively why I cannot get infinite data rates, at least not yet. I don't know if you guys know that what Albert is doing on the side. Do you guys know what Albert has a side project? Albert is working on a system to produce infinite power. Okay, obviously he's not successful. Okay, and that's why he's teaching C. Right, Edward? So the point I'm trying to say is this, is that number one, we do not have, right, an infinite power, or we don't have yet. Albert is not successful. Okay, I'm glad you guys knew that was a joke. But the goal is this, because I am what I call power capped in a system, there's a maximum power I can transmit because I can say this, right? Yongju, would you like a system, right, where you can transmit at infinite data rates, but your cell phone will last you for 5 seconds? Obviously, that's not going to be a good user experience, true? Right? You have a 5-second use of burst, right? And you get a 100 gigabits per second burst in 5 seconds. Okay? So we're going to cap the power. But at the same time, we also need to ensure, right, that there are enough gaps between each of these levels that we define so that as we transmit them over the air, right, so we need to have some minimal amount of gaps in between these guys so that as we transmit over, we can clearly distinguish between the actual level that was transmitted. And effectively, that is the bound, right, on the amount of bits we can actually transmit. Okay, and then obviously, right, we can go back and we can say, okay, well, if there's a bound, right, for sort of this amplitude, right, well, there's a range, limited range in the number of frequencies we can create. So if I want to transmit 2 bits, 2 frequencies. If I want to transmit, 1 bit, 2 frequencies. 2 bits, 4 frequencies, right? 3 bits, right, and so on and so forth. Okay, if I want to go into phase, right, well, I can go 2 phases, 4 phases, but I have a limit in the number of phases I can. So really, right, the limit on what we can do, obviously, is how accurately we can transmit, how accurately we can retrieve the signal in the presence of noise. And that is the limitation. And going forward, we're going to look at the noise, the impairments, sort of what Shankai talked about, right, the interference, right, that we'll deal into consideration, that is effectively limiting us to get infinite data rates through the system, right, until at one day when Albert successfully creates an infinite power generator. And it will not be next year. I know that for a fact. Okay? So this is where we will stop today in terms of the material. Okay? Next week, we'll recap this, right? And then go on to the other characteristics of all of these sine waves that we want to deal with. Okay? So for next week's quiz, right? Very simple, right? You should be able to reproduce a sine wave from a mathematical expression, right? Or to be able to draw a sine wave from a mathematical expression, right? Or to give a diagram of sine wave, right? And then re-express that mathematically. Is that clear? So essentially, I need you to be able to extract the values of A, F, or phase data, right? Either through a math equation into a diagram or from a diagram back to a math equation. Is that clear? Okay, and then we'll continue on with this next week as we try to unravel through all of these analog signals and digital. Okay, so the quiz, as I said, will cover up to slide 3.14, right? And if you want, you can take a look at the example, right? That just covers us to 3.15. Okay. So that's it, right? We'll end it here today. And then please, for those that did not submit quiz 1, please go ahead and submit that before the end of day Friday next week. Okay, make sure you do that.
One more question. Where can we find practice problems on this sine wave?
The textbook. The textbook has tons of it.
Okay.
Yeah, and then the solutions are all available for you.
Perfect. Thank you.
Yeah. Okay. As I said, right, officially you can get the odd number solutions, but you can easily find the even answers as well. Okay. So start out with that, practice that, right? That will form the basis for your quiz next week. Okay, so if not, I'm going to let you guys go because it's 1 o'clock, right? I want to be wary of time. I'll stay behind for a few more minutes as you guys log off, right? And I'll take additional questions if there are any. Okay, so do not forget, for those that did not submit Lab 1, please do so by next Friday, 5:30, right? I just want to make sure that you get a chance to do it. If it's difficult for you, please take a look at E.1 and E.3. Okay, next week's quiz will cover all the way through to slide number 3.15. Okay. Otherwise, right, have a great weekend. Enjoy the sun, right? But obviously abide by all of the public health directives. Okay. So you can log off and go have your lunches, right? And then I'll stay on behind for a few more minutes, right, in case there are any other questions.